Thank you, Esther. Very good to be back here in Archetri. So the talk that was assigned to me is sort of a dual topic, new trends in axion dark matter searches and alpha. I'm somewhat embarrassed because you're hearing really interesting talks on new trends all week. You certainly didn't need me. But I was also asked to talk a little bit about alpha, which is a proto-collaboration to build a large experiment at much higher frequencies looking for the post-inflation axion. And for that reason, what I'll do is just take a couple of supporting technologies which are going to be important there and pay a little bit of attention to each of them as kind of just quick brushstrokes in the way of new trends. So in fact, I've so decorated Gray's carefully drafted diagram that he probably doesn't recognize it anymore. But it's very impressive in the past 36 years now. The first PhD thesis in the cavity haloscope was Joe Rogers, University of Rochester, 1987. Walter Wunsch, also at Rochester a couple of years later, and Chris Hogman at University of Florida in 1990, really, and their faculty were pioneers here. It is really impressive what has happened in the past 30 some odd years in terms of the technology and know-how that's being built up. But it's quite obvious, and Gray pointed out, there is a huge amount of work to be done. We need to go higher, lower, deeper, and faster. But of course, you don't simply want to systematically work your way up, which might be a thing of centuries. I think experiments should be inspired. We should follow well-informed and intelligent hunches. Two of them, which were mentioned, is of course to look for gut scale axions, and you'll hear about from Chelsea later this week. And also there are these very provocative and really impressive calculations for the post-inflation axion that tell us that if axions constitute the entirety of dark matter, exotic dark matter, sigma of 0.27 or so, that would be found at a unique mass. And those calculations on very large supercomputers are becoming extremely predictive right now. And we'll need to be lucky. So I'm going to concentrate on two things. One is the higher part and one is the faster part. So the higher part as pertains to this very interesting concept behind alpha, which is the use of a metamaterial resonator. So I'll talk about first steps towards development of a metamaterial resonator. And this talk is really going to be the companion talk to this beautiful talk you heard last week from Rustam Balafendiev, who gave the theory of wire array metamaterials. And then I'll talk a little bit about progress in quantum accelerated spectral receivers. And I'll grievously violate the old maxim that Gray mentioned, which is never put anything on a slide that you don't understand, because this is really a subject for experts. So I'll just tell you briefly what's going on here, but it is really quite an impressive thing. And then I'll talk a little bit about alpha. Okay, what's the problem here? And by the way, this talk is going to be unapologetically cavity-centric, cavity haloscope-centric, and I'll talk about that and why in just a minute. Very hard problem for two reasons. One is that frequency and volume work at cross purposes. You can do clever things that can make a larger cavity operate with a good form factor and a reasonably high wavelength or reasonably high frequency, but clever only goes so far. For example, this is the haystack cavity with an annular cavity pivot. At its highest frequency, the rod is in the middle, and effectively you have a half of a wavelength, a sort of a standing wave in an annular region here of lambda over 2. That's 2.5 centimeters, corresponding to about 5 or 6 gigahertz or so. Trying to make a very large volume resonator that works at very high frequency is almost an oxymoron. Some people call it the tyranny of 1 over the frequency cubed. The other problem, which the practitioners will be familiar with, is the fact that when you do build resonators to go at a very high frequency, almost unavoidably you run into a forest and indeed even a jungle of interfering modes, mostly transverse electric modes, which at some point will basically make tuning the thing through the TM010 mode almost impassable. And I'll talk a little bit about this later on. So there are lots of other promising approaches to higher frequencies. Open structures, as Gray talked about with Orpheus and MadMax, dish type experiments like bread and so forth. I'm going to pursue the metamaterial concept as the Stockholm group proposed, simply because so much know-how and experience has been put into the cavity haloscope paradigm. All the operational know-how, the infrastructure, you don't want to lightly walk away from that. And therefore, if you could possibly persist with the idea and break the problem, crack the problem of making a high frequency large resonator that looked like a cavity, it would be a drop-in replacement for the cavity, really you should try to do so. Okay, so you heard about this from Rustam last week. Here's a traditional microwave cavity, frequency determined by boundary conditions, AKA size. And this paper by Lawson et al. Proposed the use of a metamaterial, a wire array metamaterial, that would consist of a lattice of very thin wires, radius R, spacing A, for example, and for which there's significant amount of theoretical work, and there was just a little bit of experimental work over some decades that pointed out the fact that you can basically engineer, you can design this metamaterial to have a plasma frequency in whatever frequency that you want. Won't want to go into a lot of details, but effectively, not only have you decreased the electron density here and confined it to be one-dimensional, but due to the mutual inductance of the wires, you've effectively given the electron an effective mass many orders of magnitude higher than the bare mass. And that's what drives the plasma frequency down in a metal from 10 to the 14th or so down to the 10 gigahertz range. One of the very big workers here, of course, is Sir John Pendry, one of the great leaders of metamaterials, and Pavel Belov, head of the group at ITMO in St. Petersburg, one of our collaborators. Everyone read this paper and said, gee, that's really clever. I wish I had written that myself. But I think a lot of us had a very deep skepticism on that this would ever work. And then one day the phone rang, and it was an old friend, Frank Wilczek, who was headed up the theory group at Stockholm and was on this paper. And he said, look, we're just a bunch of theorists. We need an experimental group to validate these ideas and actually develop a real resonator. Would you take it on? So somewhat reluctantly, I took it on. But I'm very glad we did. I was amazed how this thing really worked out. And I want to spend a few minutes now talking about what we've been doing and what we've learned. So what did we do? We said, okay, what had been done in the past, the tool of choice is to do transmission measurements. If I make a wire array metamaterial and I want to learn its properties and learn how to tune it, you basically do what's in the trade, in the electrical engineering trade, known as a 4-port analysis, the S21 measurements. It's basically the transmission, vector transmission through an array. We're going to build a bunch of planar wires, and we're going to stack them up. We're going to look at the properties as a function of increasing the width of this, increasing the number. We're going to change the separation. We're going to shift the relative position. And we've made a huge program over several years, working basically every day for many years now, doing thousands of measurements. We've learned some quite amazing things. So why is a transmission measurement the tool of choice? Well, one can take a slab, just like out of Jackson, and only this time it's not just it's a real dielectric, it's a complex dielectric, frequency dependent. You can calculate the functional form given the width of that thing, the loss term, and the plasma frequency. For example, this is just an illustrative example. If I freeze two of them for the plasma frequency and the loss term and increase the width there, you see you get a very unique shape for any value of the width of that from a few centimeters up to 20 centimeters or so like that. So I can look at the S21 spectrum, which you'll see really is effectively a high pass filter at the plasma frequency, and extract with great precision those three parameters. So here we are. This took me back to my youth, my first job, literally months after Sharpak and Sally invented the multiple wire proportional chamber. I was put to work at a lab in MIT as an undergraduate building wire chambers, and I found myself doing exactly the same thing with exactly the same wire, with exactly same spacing, only this time there were no antennas on the wire. There's my brilliant undergraduate, one of my brilliant undergraduates, Nolan Cowett there. And there is the array. There's a stack of 20. You can actually see half of them, the other half are shifted, with the microwave horns and the vector network analyzer over there. Now, this is a precision business. Not just anybody can build these wire chambers and assemble them. It has to be done very precisely and takes very highly skilled labor. There's my workforce. Actually, Ben came down to the lab after as a photo op when Berkeley Public Affairs wanted to do an article on him after his Nature Communications paper on his adaptive mesh refinement. So he came down to the lab. We tied his hands behind his back so he wouldn't touch anything, and he got into the photo there. Okay. So we started putting up these wire planes, 1, 2, 3, 4, 5, and measuring S21. We put in some representative values, theoretical values, and looked at it, and we said, my God, this thing actually works. It's very evident that what you're seeing is plasmonic behavior. It's really quite astonishingly beautiful. And we did this many times until we knew we were getting it right. We began to extract the metamaterial parameters, and it was quite amazing. If you put a black cloth there and you have no idea how wide, how many planes you have there, the fit actually determines the width of the array to a fraction of a millimeter.
Yeah, the color code, what is?
I'm colorblind. So these are just, we simply, the colors here, I think, correspond to the same colors on the right-hand side. And that is 5 planes, 6 planes, 7 planes. This is the number of planes. That's 40 planes. Okay. And what's astonishing is that after you've put in between 5 and 10 planes, this thin, you already get metamaterial behavior. You actually see a well-defined plasma frequency within a couple of % of the asymptotic value. And the asymptotic value, after you put in about 25 planes, many months after we did the data, we actually went back and evaluated Pavel's semi-analytic theory and laid it on there. So there was no fudging here. The agreement was at the 10⁻³ level. I mean, you could have knocked me over with a feather.
Wires are as those of wire chambers, so
it's gold on tungsten, 50 micron diameter.
Wires for gas
it just took me back to my youth. Most importantly here is we wanted to extract the loss term, and we found that after about 10 layers, it asymptotes down here. And if you calculate what the Q is for that, due to the internal loss of the array, it comes out to be about 220. You would calculate it theoretically about 260. And you'd say, well, that's no good. You can't build a haloscope with that. But if you go back and you look at Rustam's paper from last year with the ITMO group, and they actually did a study to say, okay, for any given frequency, you can pick the combination of radius and spacing to optimize Q. And it turns out to do that, they wouldn't be 50 micron wires. They would be, a couple of millimeter rods, and the Q would be 4,000 plus, which from our experience with resonators like that before, at cryogenic temperatures would be above 10 to the 4th easily, and you're in business potentially. Okay, so then we say, okay, what do we do? Is this possible to engineer this thing to tune it? Well, the first thing you would think about is changing the spacing of the planes. Here, by the way, are the fits, and you can see that if I change the spacing of the planes between 3.2 millimeters and 7.6 millimeters, you can actually see the plasma frequency march down. The dotted lines indicate the plasma frequency for each of those spectra. And again, you see perfect agreement with a semi-analytic model at about the percent level, and you get about a 50% dynamic range. This is not the thing, of course, for a haloscope. You know, when you build or procure a very large magnet, you want to use all of the magnet all of the time. You don't want your detector to be going in and out like an accordion. It presents us lots of practical issues. So how else might you tune it? What we did then is to gang together the alternate planes such that you had two interpenetrating lattices, and then basically mapped out or explored the whole space of the overlay of these two lattices from a rectangular lattice to where you actually even had the wires. Here's like a rectangular lattice with half of B, so there's wires here. And then we move in this direction, and you can see from going from this position to this position, for the larger array, you get about a 16% dynamic range. If you go from the highest frequency of this larger array, A and B of being 5.9 and 14.1 millimeters, from the highest frequency to the lowest frequency, again, you get about 16% dynamic range. These are certainly very fine kinds of dynamic ranges to contemplate in doing a haloscope type experiment. Now you might say, okay, here when the wires are far apart, you're getting agreement at the few part per thousand level, but here when the wire planes really begin to approach one another, the errors tend to be a percent or a few percent. We don't blame our theoretical partners on this paper. It's after several years of doing thousands of measurement, the wire planes have gotten so beaten up that the wires were really not completely taut. And when you think that the wires are really 100 microns apart, they might be 150 or so. So this, I think this is really the fact that we were dealing with tired wire planes, and which is why we didn't see such deep minima here as well. Let me come back later on to what a real resonator might be when we want to take a first stab at 10 to 20 gigahertz. The other problem here that I alluded to is a more mundane problem, a nastier problem. It's one thing to have a beautiful concept to jack up the frequency, but the real problem, and the practitioners in the room will know this, if you look at cavities down in the few gigahertz range, you tune the TM mode, usually by swimming around a tuning rod inside the cavity, and the TE modes are relatively immune to motion there. So the TM and the TE modes cross one another. And you might say, well, should I be concerned about that? And it turns out sometimes they are benign crossings, but more often than not, they undergo hybridization of the modes, and it wipes out a certain range of frequency that you have to just knock out, and if you care to, go back and fix the problem later on. In the few gigahertz range, the problem is a tolerable few percent. If you look at this cavity, we built Maria Simonovska's thesis a few years ago, which will be deployed in Haystack later this year. You see the TM010 mode like that. You see the TEM manifolds, but you see lots and lots of other mode crossings there. They're the ones we actually have gone through and mapped them all out. Now you're pushing up to close to 10% that becomes problematic and has to be filled in some other way. By the way, just an editorial statement, the best form factor and therefore the best figure of merit, if at all possible, preserve symmetry to the degree you can in a cavity. This is a nice Swiss watch cavity that symmetrically moves out 6 rods like this. And now if we actually go back and put in a smaller diameter rod to go up to something like 12 gigahertz, we've done an initial measurement there, And sadly, it's exactly what it looks like in these simulations, which took a few months to do, tiled like this. You can see, I call it the where's Waldo problem. You can say, where's the TM010 mode? It's actually worse than that. Once the level density gets so high, there is no a separate identifiable TM010 mode. Its strength is actually fragmented into in the neighborhood of modes around it. And you say, how do you know these things? We know those things because reaching back into the treasure trove of microwave lore that was developed during the radar project in the war, Julian Schwinger and David Saxon developed this technique for mapping electric fields inside cavities. This is a tool of the trade in the accelerator business called sort of bead perturbation technique, where you simply have a stepper motor and run up and down a tiny little sort of millimeter bead of sapphire epsilon of 10, or if you want something smaller, you can use polyethylene epsilon of about 2 or so. And the frequency shift here, you can see here you get an avoided crossing. It's just like two-level mixing in quantum mechanics, exactly the same thing. And you can track these modes as they approach, and you can see you go from a pure TM010 mode, longitudinally invariant, and here's this high order TE mode. They're separate and well identified like this. Once they begin to come close to one another, they've hybridized and the problem is a mess. And then later on, they separate, and this one becomes the TE and that becomes the TM. In the region where you have high level density, the situation is lost. So what do? Well, the other thing we've been working on for a few years is, again, reaching back into the playbook in photonics and accelerator physics. It's the old idea of Ilya Yablunovich, actually, of Berkeley faculty, recently retired, became very famous with this, is the photonic band gap structure, where you can form a lattice, rectangular, square, whatever, and then calculate, what is the properties of this lattice in terms of propagation of electromagnetic waves through it. And it turns out you get, just an analogy with solid state physics, there's basically a band theory to it. It's just like block waves in a condensed matter environment. There was I actually took on a grad student from the Temkin group at MIT, Samantha Lewis, now taking up a faculty position this fall, who had already had several years of experience in papers as an undergraduate working with photonic band gap structure. So this was exactly what we needed. So the idea is that if you take a lattice like this and you form a defect, i.e. you remove rods in the middle of this thing to leave a cavity, and you choose an operating point. An operating point is a ratio of the radius of the wire or the rod to the spacing of it. Going from 0 to 0.5, it turns out physics is very much on your side. So this upper panel here shows for the TM modes, this is what we call the Christmas tree diagram, is the dividing line between the disallowed region where TM010 modes cannot propagate through the lattice, and to the left is where they can propagate. Now, for the same operating point, the TE modes, it's the flip of that. Everything here is allowed except for relatively small islands where you would be able to propagate freely. So what have you done? You've created a structure, pseudocavity, which traps TM modes and passes the TE modes. So if everything works out correctly, what you've done is actually created a structure that could completely burn down the forest of TE modes and leave the TM modes able to march up and down without any interference. We've done a lot of work on this. This is an early prototype. This, for example, I did not have the panel of both the simulation and the measurement of a solid barrel there, but there were many, many modes up and down here. But both in simulation and measurement for the PBG, you actually see perfect agreement, and you see absolutely no other modes in the spectrum. We then became bolder and say, okay, suppose we put a tuning rod in there and break symmetry on the inside. We've just finished up those measurements and are about to write up a long campaign of measurements. And it turns out breaking symmetry inside the cavity part of the photonic band gap structure is not a problem at all. It's completely unaffected. And if you look back here, you might say, well, I would never put that thing in a haloscope. That looks very large and awkward, and I've used up most of my space. But it turns out you can actually keep the same operating point by going to the same ratio of radius to spacing and go with much smaller rods. And you can even break symmetry again and turn it into a circular pattern. So it's not really a perfect, a mathematically perfect lattice. So you've cheated a little bit. You can make the thing very, very thin. You can go down to basically 3 rods in the stockade, and it seems to work. And we're about to do a final test this coming month where we're going to dress the 7-rod cavity with a photonic band gap structure rather than a barrel. And if it works, we're actually probably going to be the next run coming up in Haystack. We'll probably be using for the first time ever, a photonic band gap structure and be able to go up in this range here and see none of that, but just be able to track the TM modes, which all move in concert. The shoe hasn't dropped, but I think we're relatively optimistic that this strategy that we've invested in for a long time is promising and likely to work. So what is a prototype metamaterial resonator look like for the 10 to 22 gigahertz range? And we're doing something which is roughly of the same size that could go into Haystack. And it looks something like this. On the inside, you have the metamaterial, my fingers here, structure. We've put the rods in what are called dyads on a common axle at either side, 2 rods which can rotate like that. All these rods rotate in concert. And then on the outside, you see a denser pack of rods, which is the photonic band gap structure, outside of which you would have a microwave absorbing material to make sure that the TE modes did not reflect off the thermal shield on the inside of the magnet and come back into the structure. And there is one of Rustam's simulations for what this thing would look like. This particular geometry goes from, I think, about 9.6 up to, or 9.3 to 11.6 gigahertz. You might say, why, rather than having the rods, the dyads, stay vertical? You can see if you look at any particular pay, they remain vertical. Why is the cavity here or the structure tumbling? And it turns out if by chance, we'll come back to this later, you were to have a horizontal Bohr magnet, the simple way to make all of these rods move in concert is not to make the rods move at all. You simply counterweight them to keep them vertical and you tumble the cavity. If you're given a vertical cavity, you can still do this in a relatively simple mechanical way, but gravity is your friend in the case you have a horizontal Bohr magnet. Our friends in Stockholm, literally, this is quite impressive. About 4 or 5 years ago, they were a theory group, but the whole thing of the concept of this metamaterial resonator for the post-inflation axion really has kind of catalyzed this group, the metamorphosis into this group, into kind of an omnicompetent group that's really up to speed and I think really quite world-class in terms of resonator development. They're now doing conceptualization of resonators, theory and simulation, prototyping. They're doing very clever things with 3D printed cavities. They're working on some very interesting antenna designs and doing a lot of engineering. And here is something Rustam showed last week, which is the idea of making sort of ganging together two rows of rods and using the degree of freedom that gives you the largest dynamic range, which is to bring the rods from maximally spaced to close proximity. And in this particular resonator, they're getting about 33% dynamic range. Okay, so let me change gears now and see how we're doing. Okay, I think we're going to be fine. So as Gray was mentioning, you know, the scan rate goes like the inverse of the temperature squared. So there's a huge premium in these experiments, which really struggle to get their sensitivity in the best of circumstances to really drive down the system noise temperature. And over the course of the haloscope paradigm, in the early days, Pierre will remember, we were dealing with the best amplifiers in the world were HEMPs that had 5, 10, 20 Kelvin noise temperature. ADMX, we had teased John Clark at Berkeley into the pool, and he developed these microstrip coupled squid amplifiers, which all of a sudden turned quasi-static devices into gigahertz amplifiers. It was just a huge development in the late 90s. And all of a sudden, we were off and running. And so squids in the gigahertz range were the first device to be used, quantum type device to be used. JPAs came by, which were even better and worked at higher frequency. In Haystack, we're privileged to have the Colorado group, Conrad Lehnert, as part of our team. He's, maybe the premier guy in terms of quantum sensing for fundamental physics in the business. And, we started running in 2015 with a JPA at just twice the quantum limit, just a couple of photon occupation number. But already he was thinking that there was another frontier, which was to employ squeeze states of vacuum to increase the scan speed here. And again, I'm just going to give a very broad brush approach to this because this is not my seminar to give. This is really for Conrad and his people. But the basic idea is the following. If I represent a microwave cavity, sort of from a circuit point of view as a 3-port device, where I have a port which is simply a representation of the axion signal. I represent the loss term in the cavity as simply a grounded resistor there, which of course also is at a finite temperature is a source of noise as well, and a measurement port. As you know, in the microwave cavity, if I plug anything into the port of the cavity, necessarily there is basically dark noise going into the cavity greater than an irreducible half quantum of noise. And then of course that goes in and the axion signal for a simple device with just an amplifier hanging off the cavity would give in a period of time random phase kicks in a classical sense to the noise, and then it would be read out normally through going through a circulator and out to the post amplifier. In sort of quantum measurement, the noise can be represented as a sine-like and cosine-like component. Those operators are non-commuting, and therefore there is always an irreducible 1/4 H area here. And the situation, of course, that area of that blob is higher if this thing is operating at finite temperature. If one squeezes, which JPAs do quite readily, one can actually use a 2-JPA squeezer where you prepare the noise in a squeeze state through the circulator, which is injected in here. So I've squeezed this blob into an ellipsoid. Now, in the time the noise is in the cavity, you can see the green bumper around there represents the growth of that area by the axion signal. And then it is read out, and then you squeeze 90 degrees out of phase with that. And one can see that if I look at the major axis of the green to the major axis of the red, compared to the unsqueezed state, that the signal to noise has gone up. On the test bed that was built up in 2017 at Colorado at Gila, they had predicted and achieved exactly what they predicted, which was about 4.5 dB of squeezing, which would give about a factor of 2.1 speed up as well. And here, in fact, you can see a representation of the noise as they change the phase between the squeezer JPA and the amplifying JPA like that. And at pi over 2 and 3 pi over 2, you get a dramatic drop in the power spectrum there. So they did a mock axion experiment where they had a synthetic axion that was injected at random frequencies. And they did 3 cases here: squeezer off, typical overcoupling, beta of 2 and no axion; squeezer off with the axion on, and then squeezer on with the thing largely, or with the system highly overcoupled. And you can see what's happening. The measurement noise comes in, and if it's not right on frequency, it's maximally reflected off the port. So it's kind of the anti-Lorentzian. In the case without the squeezing, this is the measurement noise. They've driven that down by the ratio of the variances with the squeezer off and the squeezer on. And you see you get a large gain if this is the cavity Lorentzian there. But the situation gets better. Given that you've dropped this down so far, you can overcouple the cavity such that the Gaussian representing the Lorentzian representing the signal and the internal noise coming out of the cavity, and the anti-Lorentzian showing the measurement noise reflected off the cavity, both get very broad. And what you find is that the span over which the internal noise, which can be driven down as much as you want by cooling of the cavity, the span over which it dominates over the measurement noise is much, much broader. And it turns out that's the gambit which allows you to accelerate the experiment. So this was then, a twin was built up at Yale, and it worked exactly as the predictions and what was achieved at Colorado, and we got a factor of 2 speed up, and we've actually published that in Nature a couple of years ago. And this squeeze state receiver has been in routine operation. We're now on our 4th run, with 2 more runs being planned in 23 and 24 since 2018. It's really entered into routine performance now in Haystack. There's a picture of the little test bed at Colorado. There's Dan Palkin. This was the pseudo cavity they had there. As you can see, it was not the full Haystack cavity, but it was just a very small cavity, single mode cavity operating in the 7 gigahertz range. Okay, now this I'm going to spend very little time on. Just when you think you couldn't be more astonished by the quantum wizards, we're now more astonished by the quantum wizards. It turns out Conrad was already thinking ahead. How do you improve on that scheme? And the scheme that's been developed by Conrad and his students called Ceasefire. Kelly Wirtz, his graduate student, came up with this during COVID: cavity entanglement and state exchange for improved readout efficiency. And here I'm not going to go into a lot of details because I'm way beyond my headlight here. What you're doing now is you have 2 cavities. You have the conversion cavity, and this thing up here is a kind of a pseudo cavity. It's an onboard or an on-chip cavity up in the field-free region where we have the amplifiers connected by a rigid transmission line here, basically a very small waveguide. Notice what we've gotten rid of. We've gotten rid of the circulator, which is noisy. Circulators, if at all possible, you do not want to put in the unamplified region of your device because it does introduce noise. And what one basically is doing is one is creating an entangled state between this cavity and this cavity. One has these 2 cavities, and one drives them, one modulates their coupling, one modulates this transformer, this mutual inductance between this cavity and the first cavity. So you basically modulate the coupling between them simultaneously at 2 frequencies. One is the The difference of those two cavities, they're slightly offset in frequency, and the other is the sum. The sum of them simultaneously squeezes both modes. The difference of them entangles them. So you entangle and squeeze, and lo and behold, what happens is that you ultimately measure, you're able to push effectively the entirety of the signal into the receiver chain, accepting a very small irreducible h/4 area here, and then down in remaining in the axion cavity here is all of the measurement noise. They're now exactly where they were about 2017. They're building up their twin in Boulder. They're now doing measurements. It seems to be performing as it should be. And when they finally give the thumbs up, the Yale twin, which is the same thing, plus magnet, will be built up on that side, and then will be go into commissioning and operation. They theoretically, you can get about a maximum after a fixed 15. The exact incarnation for this device is predicted to be a factor of 8. What they've measured is 5.2, given the components and so forth, the design they have. But I think they're confident they, in their paper, said that they could do a factor of 8 in the design that would be deployed at Haystack. Okay, in my remaining few minutes, I want to talk about, I think the time is perfect, the Alpha Consortium. This idea came out relatively soon after the Lawson et al. Paper. Say, okay, this could work. Let's get a gang of like-minded people together. It's not a collaboration. There's no funded construction project yet. The affiliation is open. No governance structure except a steering committee, but we have been in a rather disciplined cadence for several years of having bi-weekly meetings where they used to be more granular. We used to have an antennas meeting and a superconducting wires meeting and so forth. We've now aggregated them into a bi-weekly theory meeting, a bi-weekly experiment meeting, and then also bi-weekly a meeting which alternates between the overall consortium and the steering group. And we've kept up that discipline for several years now, and it's actually proved very effective. The meetings are always at 5 p.m. Central European time, and so those of us in strange places have to be up early or late or something like that. We've had 2 meetings. One was a virtual meeting during COVID organized by Arizona State. The other, we actually had an in-person workshop at Oak Ridge last October for reasons we'll point out. And the Swedish government and the Newton Alice Wallenberg Foundation have paid attention to this. In fact, are now beginning to fund the Stockholm group in a relatively good way. Gudmundsson has now recently moved. He has a split appointment between Stockholm and Iceland, where he has a faculty position, and has a European research community grant, committee grant for his startup of his lab there. There's the meeting we had at Oak Ridge. There's Marcel Dimotot, who is the physics division leader there at Oak Ridge. And several people, my own group there. Okay, because it's kind of a loose and open thing, it's hard to say exactly who the consortium is, and it really at this point doesn't matter. But there was a white paper published that was pulled together by Alex Miller, then at Stockholm, now at Fermilab as a postdoc. And so this is a very rough list of institutions, of people for whom this was important enough that they put some skin into the game and wanted to help write this white paper, which gave a summary of all the work that had been done so far and pointed to future directions for research and engineering. Okay, prospects for an experiment. Well, Marcel got into this because he rang up a couple of years ago and said, gee, you know, the neutron scattering center in Berlin, the Helmholtz Forschungszentrum Berlin, the reactor was shutting down, and a deal was being made. It was been floated to give this prodigious magnet they have. It was built by the National High Magnetic Field Lab in Tallahassee. This is the outsert part. There was also a conical bitter magnet there, which boosted the field up to 32 Tesla over a very small volume. It was a huge project. It attracted a lot of attention among the magnet community when it was being built. And they said they're willing to give this magnet to Oak Ridge in exchange for beam time at the spallation neutron source. Now, the new building and the new hutches or the new beam lines at the SNS won't be ready for more than a decade. So he said, look, the magnet is ours to use, free to use. Would you like to contemplate Alpha being built up around it? And of course, we were on a plane relatively shortly after I went out there to give a talk and to look at the hall and things like this. Now, there was optimism that the magnet would be transferred in 2023. It turns out the labs have agreed. The labs want to do this. Oak Ridge has said, we're doing this. The lawyers, of course, have to sign an MOU. And of course, that just always holds up things there. It's a very significant magnet. It's a 13, the outsert part is 13 Tesla, 50 centimeter bore, and 170 centimeter length, 1.7 meter in this direction. And you can see the axial field profile here. Available for 10 plus years. Now, it's not ready to go. It's not plug and play. This is a very unusual magnet. It's very low inductance, very high current. It's going to take a significant amount of investment by the lab to get the thing set up. Right now, they're just trying to figure out where to put the thing until they can actually choose a hall to set this thing up as a facility. So we're still far away from using this thing as is. If things get too far pushed out into the future, we actually recently, some months ago, became aware of and actually have an offer, indefinite offer to take as long as we want, a 16.4 Tesla medium bore magnet that we could use to get going early with a slightly smaller version. I've been asked, I was reminded, to advertise an assistant professorship at Stockholm University in axion physics. You know, there's a huge shift in the community from WIMPs to axions, but I kind of grind my teeth because universities are conservative. They're still always posting faculty positions for WIMP searches, and I'm just shaking my head what these people are thinking. But finally, Stockholm has come forward and said they want an assistant professor. It's actually in astroparticle physics, but with a strong axion theme. In fact, they actually would like this person to be willing to work at least in the early phases of their career on the alpha experiment. And what they are very insistent about is they really would like the application of female applicants to this position because as it mentions here, most of the teachers of the department are men. So this is a wonderful opportunity. It's tenure track. Note that the closure date is June 15th. People I know who have applied for it have said there's several forms that need to be filled out. It's a little more complicated than applying to a US university. But I think this is a great opportunity. Think about it, let other people know. And with that, I'll wrap up. I would just say that the metamaterials, we've passed a first test, not a last test. There are many other questions remain opening, like coupling to the metamaterial. Can you make, as we will probably need to make it, particularly at higher frequencies, this thing work in a magnetic field with superconducting wires? How well does this thing cool down? Can one really kill the forest of TE modes? All that, but I'm confident we can beat these problems. Quantum sensing for ultralight dark matter, I think we're out of the exploratory phase. You know, I think this has now become, at least at the level of squeeze state receivers, this is now a mature tool. I think experiments should be doing this. It does require that you get everything else in the system noise temperature down to be productive, but I think we're already there. The future is already here and it's going to get better. And alpha is in a formative stage. We need new ideas and commitment. Please join us, and we're going to have new some workshops coming in the future. So with that, I'll quit.
So thanks a lot, Karl. Any questions to Karl?
He wants his job back.
Thanks for the nice talk. Yeah, so with Alpha, are you at the stage yet, if you get this magnet at Oak Ridge, of being able to make a sensitivity projection as sensitivity as a function of mass, or is that too many steps away in terms of like knowing which frequency range?
We didn't. Well, let me just put the following. I think the sensible thing, and I think it accords with theoretical prejudice, you want to start low and go up. So I think the first target would be 10 to 20 gigahertz. Given the size of that magnet, and we've looked at a number of different type resonators, there's no question you'll get down as far into the QCD band as you want. We'd like to be able to also scan that range fast. The broader question you're asking is, are we ready to go in terms of construction? We actually had a student at Colorado, a mechanical engineering student, with people at Oak Ridge working on a conceptual design for what the overall thing would look like. Life in the horizontal world, as you've learned from Gray, which is sort of a new paradigm for haloscope. So we actually have gotten a little bit of a head start on what that would look like as a mechanical design as well. Would we be ready to start a construction project tomorrow? No, but if we were given the green light, we would get there soon.
So you'd actually get to the QCD axion.
Oh sure. I mean that's a monster of a magnet.
Yeah.
There's no question about it.
Yeah, thanks for the very nice talk. I have a question about the slide where you showed the plot where you couldn't, where the experimental data didn't quite match the theoretical prediction. So you said that was most likely due to the wear and tear of
the wires.
Of this wire. Yeah, exactly. So do you expect that to be a problem for the operating experiment? Is wear and tear like
no, because
or is it just because of the type of tests and
because of the fact that there it is. We wouldn't be using these wires at all. The optimization of Q would be not few millimeter and 50 micron wires. They'd probably be sticks or rods of copper spaced by something on the order of a half a centimeter or a centimeter.
Okay, so that's basically stable
now
over the lifetime of
the question no one asked is, okay, fine, you could build something the 10 to 20 gigahertz range. What is the world of 50 gigahertz looks like? Then you're in the world of doing something which is really almost going to be almost a foamy structure. It is going to be wires and closely packed, and there it's going to be fragile, and there's going to be a whole host of mechanical and materials issues.
Thank you. So yeah, to sort of follow on that, when it comes to these metamaterial cavities, it seems that one is not expecting the losses to be dominated by, resistive losses in the wire, right?
Yeah, that's correct, because if you do move to the appropriate size rod for the frequency wire, quote unquote wire, then that would not be the issue. By the way, I did not mention this, but in case it was not clear, you would not put this thing just kind of in open air. This would exist in an enclosure, both because you need to shield the thing from RFI, the radio frequency interference from the outside, but this is what you would fill the entirety of a cavity with as well. Now, Frank Wilczek makes the point that if you have an axion field driving uniformly, spatially invariant, if you had a perfectly conductive large array of superconducting wires, the mode would in fact be trapped in there. It would not radiate away. But that's, this is the thing, we need to be putting this thing into a can and then in the usual way, making engineered features for couplers and so forth.
Okay. So naively, my expectation is the Q would increase with volume in that case, but I'm not sure if that's correct.
Let's see, with Q,
if your
yes.
if your losses are dominated by the walls, you make the volume bigger.
Yes.
Yeah.
By the way, we are starting a program, in collaboration with Johns Hopkins, on doing tests of arrays of quote unquote wires, rods, making resonators out of superconducting materials. Stephen Anlager, who's an expert in this in Maryland, he's one of our gang, has been in this business for years. He's actually made superconducting wire array configurations inside of a waveguide and done these measurements, not at field, but we already have a little bit of a head start on working on these things. Also, the lateral walls parallel to the B field can be type 2 superconductors as well, not the end caps. Thanks.
More questions in the room or in Zoom? I don't see.
So I have a question about squeezing. In theory, you can squeeze as much as you want. So what is the technological obstacle in increasing squeezing?
Ultimately, it's the loss. You have to work on the transmission loss cavity.
Thanks.
Okay. If they are not,
I have a very naive question also about squeezing. So you guys are doing squeezing with Haystack and getting these big improvements. And ADMX at lower frequencies is not, I guess, but is it frequency dependent or like other sources of noise dominating ADMX? Can this eventually help speed up? I mean, is there a physics difference between these high and low frequencies that? Mhm, mhm.
But whether or not it's practical at this point, I won't represent it very sure.
Right, so for one, the standard quantum limit increases linearly with frequency. So at higher frequency, you hit the standard quantum limit sooner. And so it's more important to do squeezing. And also you're, for the same fridge temperature, you very quickly. And so it's important to move to squeezing at higher frequencies. At lower frequencies, so what am I working on in ADMX right now is I could push the physical temperature down. We spend time doing just better cryo engineering as opposed to squeezing, and that the payoff for now is better there. Well, yeah, as we move up into higher frequencies, it's the standard quantum limit just rises from the floor and hits you in the face, and